Good morning, and thank you very much. I'm delighted to be here, and I would like to thank our host for inviting me. In this talk, I will be focusing mainly on a topic that I think is quite gaining more interest in industry, namely 5G spectrum sharing. But I will start with giving a little bit more also outline of where we are in terms of standards and spectrum 5G. What are the timelines? What are perhaps the most eminent use cases that we are seeing in industry? And then I move on to share with you some recent research on 5G spectrum sharing. So, but before that, as was mentioned, I have moved recently to University of Sussex. I'm heading Department of Engineering and Design there. And so I thought I'd give you a very short overview of the sort of research that we are doing at Sussex. So, and the structure there. So we are part of the School of Engineering and Informatics. And my department consists of a number of research centers. And these research centers, roughly the areas that are covering is digital signal processing and optics, so that's I squared SP. Then we have a lot of activities in terms of sensor technology, including sensor for wearable devices, plastic electronics, and so on. We fabricate some of them in-house, as well as 5G and mobile communication. Then we have a large center on thermofluid mechanics, and it's looking like engines, turbine engines, and large engines, and so on. A lot of work with GE there. And a very flourishing area in sort of a dynamics control and automotive, which also includes areas such as robotics and autonomous systems. And then we have product design. And very recently we were fortunate to have funding from UK government, hefty funding, to 5 million, plus 5 million from the university. We are just about to establish our future technologies laboratories, which is together with the Department of Informatics, and that will be focusing on robotics, mechatronics, electronics, and computing. So those are some pictures, and of course 5G is also an area that we are covering. It's quite new. But my role here is to bring 5G connectivity in those areas such as automotive, such as robotics, such as wearables, and so on. We are very much industry focused. We work very closely with industry, either through collaborations or through bespoke industry research. So these are some of our current sponsors and collaborators. We are also the only UK academic that is a member of 5G PPP, the 5G Infrastructure Association, which is the European EU's Horizon 2020 program, which is industry-led and is deriving the 5G R&D and now moving towards trials. So we are the only member, one of the few academic members also in Europe. Now moving on to the content of talk, I will briefly just say where we are in terms of standards and spectrum roadmap. The standards are obviously moving very fast, and it's very good to be aware where we are with standards. Then I highlight a little bit one of the 5G, pre-5G or not, could be 5G, the way standards moving use cases, which is becoming very, consensus is building industry that this is going to be the first prominent use case, especially in millimeter wave bands. And then I will discuss 5G spectrum sharing and conclude. So in terms of a standard, well, the 3GPP standardization work is moving very fast. As you know, basically initially it was planned that we could have the standard work. So it's accelerated now, and basically if you look at this time schedule, we see that by the end of so we are there, and then what is happening is that the first version of standard for 5G new radio is going to be finalized just at the end of this year, and that will be 5G and our non-standalone, meaning that sort of millimeter wave physical layer and so on. They will be basically a data tape that will be then anchored into LTE really, and this has been an acceleration, which is very important, and it's very timely because we are having also the Olympics, Winter Olympics in Korea starting and so on. So, so in that sense, the first version is going to be ready, but it's non-standalone. And then the 5G new radio standalone is going to then be finalized by the end of so about 6 months later, and then after that we move on towards obviously the study item is also continuing. So the first phase of 5G is going to be mainly enhanced mobile broadband with some components of ultra low latency, so shorter TTIs and so on, but the focus will be mainly on enhanced mobile broadband. And then the second phase will be more focusing on massive machine type communications and ultra reliables and ultra low latency. So this is the sort of the way the standard moving very, very fast. In terms of a standardization process, this is also in the process. So where we are here now in 2017 timescale, that's that ITR is looking at basically spectrum sharing issues and so on. Proposals for evaluation and consensus building is going to be in 2018-2019 timescale, and then but that time is 3GPP also in a position to basically provide the proposals to towards IMT 2020 with WRC 19 and then the allocation of spectrum bands in WRC 19. So basically what we are here in terms of a spectrum, we are now at the moment a timeline with a lot of work is going in terms of studies of coexistence and sharing between different services. And I think that that's a very important area where we are also very interested. Now moving on, well, there's a lot of discussion about what 5G is going to be and what it's going to do. This is all obviously consolidating very nicely. In terms of use cases, what we are seeing is that one of the probably the most important, and it just consolidated only in the last year or so, is the fixed wireless access or fiber-like broadband using the millimeter wave frequencies. And it is interesting because obviously when I was at Samsung, this was ongoing and so on. But last year in December when I was in Globecom, which is one of the prominent conferences, IEEE conferences where a lot of industry attend. I was fortunate to also share a workshop with colleagues from Huawei and so on. And you see that there is an emergence. So if you look at these stars from Dr. Wang, you see that he mentions it's maybe small about fiber-like, basically fiber-like millimeter wave access is going to be, basically is going to be the first use case or something like that. So it seems that it's happening. Verizon is obviously working on trials and so on. Some UK trials happening, I think, with Samsung and Arqiva and elsewhere. And this is very important for millimeter wave technologies because obviously it is a fixed access. So this is just an example of sort of architecture. It looks like so you have millimeter wave base stations that are then connected to fiber, and there could be some of the functionalities also. Sort of CRAN-like functionalities into a Mac and so on, and then you provide broadband access from outside to inside. In this case, in 28 gigahertz to small user equipments, small base station, small access points that are just inside. And the good thing is obviously is that in comparing with fiber that requires less labor, material, and so on. The logistic challenges, the need for cables and digging, but also this is a very important initial use case because a lot of interesting research challenges that are in millimeter wave frequencies, such as coordination of interfaces, interference, and scheduling of beams and so on are already embedded in this technology. For example, one of the things you can get is that although in millimeter wave frequencies, because of the narrow beams, you have a much better focusing and therefore in principle less interference. When you have a dense deployment, multiple millimeter wave base stations can actually schedule the beams such that there is some possibility for beam collision. So for example, in your medium access control, you need to be very careful about coordinating the beam. So I think this is definitely one of the most prominent use cases, and also obviously much more is going to be demonstrated in the Olympics in Korea and so on, but this is probably very prominent, very important for millimeter wave bands. In terms of a spectrum, these are basically new spectrum bands that are under study for 5G above 6 gigahertz for WRC19. On the left-hand side, we have those that there is a mobile allocation already, and on the right-hand side, those that there is no mobile allocations. Obviously, this doesn't include the 28 gigahertz bands, which is this sort of regional in US and Korea and elsewhere. The band that I've highlighted in green, it's been, and that was part of the work that was also done in 5G PPP, is now considered as a 5G pioneer band. So this is the band that a lot of trials also in if millimeter wave in through 5G PPP and others are going to happen. And obviously this band is also adjacent to 28 gigahertz band, which is so there is a satellite allocation. So coexistence studies, for example, very important there to look at interference and so on. So these are the bands, and it's very interesting in terms of a spectrum to look at, what is the roadmap. And if we look at the US, this is very recent. This is from Bloomberg. So the spectrum holding of various operators in US in the millimeter wave bands. So this is 28 gigahertz and 39 gigahertz. Now this is so Verizon had quite a large amount of that, and then a company called Straight Path. I don't know if you had heard that news. This was actually a company set up by some of the people coming from Samsung, and this was brought by Verizon last week following bids by AT&T and both Verizon. So you see that basically the battle for millimeter wave spectrum is hotting up, and then you have obviously other operators that have, but I don't recall the amount, but it was quite substantial, and it's clear that there was a battle about acquiring more millimeter wave bands between AT&T and Verizon. So a spectrum is extremely important. I think this spectrum, millimeter wave spectrum, is very important. How about spectrum sharing then? This is an area that I've been researching for quite a long time. So as of interest, as now I'm in also academic research, I have a big interest in spectrum sharing. It's a very important area. But also the European Commission and regulators are looking very much into, do we need to allocate spectrum the same way as we did before? Has it business as usual, or there are opportunities for sharing, for example, maybe localized sharing and so on. And I'm highlighting two aspects of spectrum sharing. One is the sharing of unlicensed spectrum. So this is a continuation of sort of LLA and so on that was already started in 3GPP. Now the problem there was that the Wi-Fi was already in these bands. Wi-Fi had very good sharing mechanisms, so CSMA, CA and so on, they're all designed for fair sharing. And then in my view, when LTE came in, this was like an add-on to try to use listen before talk and other mechanisms to enable this fair sharing. But now, as we see, and Qualcomm obviously have been one of the key players here, this is very recent, is that now there's a new study item in 3GPP that is looking at sharing for 5G. And in that sense, one of the important aspects is that if you look here, they also considering standalone unlicensed use, which means that unlike LLA, where again the use of license bands, the use of ISM bands was by LT was anchored to LT. This can be even a standalone, so very similar to how Wi-Fi operates. And I think one of the prominent areas this is going to be is probably the 60 gigahertz bands, which is technologies such as WiGig operating there. Therefore, sharing of 60 gigahertz band, I think is a very interesting area too, because also unlike, as far as I know, this lower Wi-Fi band, the coexistence mechanisms are not very well defined there. So if you have a new technology coming in, there is more opportunity to enable this sharing between cellular technologies and mobile. And why sharing in millimeter wave bands? But there are a number of very interesting aspects if you look at millimeter wave. First of all, in millimeter wave, how much time do you have?
We need to break at 20 past, so we've got another 10.
Okay, that would, thank you very much. So basically, when you go to millimeter wave bands, obviously, if you want to enable long distances, I mean like 100 or 200 meters and so on, then obviously you need to use beamforming. So beamforming actually a mandatory feature, for example, in 802.11ad, both transmitter and receiver. In 5G new radio, this is also going to be, is in the process of being standardized, both non-standalone and standalone. Therefore, beams are a sort of a new resource that can be used for sharing. It's a new dimension that enables sharing of a spectrum between multiple, either same or different systems. And if you think about it, obviously this is very theoretical, it's not in practice, but if the beams are extremely narrow, then you go to infinite sharing in principle, because we are going for two-dimensional spatial sharing to a one-dimensional one. Obviously this is not really the case, but that's a sort of upper limit. But then there are also new interference scenarios that I mentioned, that if you have very narrow beams and you have a dense deployment, you could have things like beam collision. So also new mechanisms need to be done. So this is basically the scenario for spectrum sharing if that happens in 60 gigahertz bands. So you will have basically, obviously, systems such as WiGig and so on operating there. There were already a number of work about outdoor WiGig base stations, hotspots. Then obviously multiple operators using 5G unlicensed can be using that spectrum. So it's a scenario where you have multiple technologies, multiple access technologies, multiple operators, and so on. Therefore, a sort of coordinated beam scheduling or interference control is not the way to go, because these systems simply have different access technology and so on. But it seems that we are able to, and this is some initial studies we did, that looking at this scenario, and basically you could use mechanism similar to some machine learning and learning algorithms and so on, in order to basically enable each of these base stations here without any coordination between them to basically be able to schedule their, coordinate their beams. So the scheduling of the beams such that they are able to avoid interference between themselves. So it's a distributed beam scheduling. This is showing a sort of a simulation scenario where you have, in this case, two base stations, each serving multiple UEs. Using beamforming, we also looked at a larger one. And then basically this mechanism, so it's sort of a learning mechanism, can converge to kind of a quite good solution. These are some examples of how this works, basically. So obviously the worst case scenario is that you have multiple base stations and they just randomly schedule their beams. So means the sequence is random if you have multiple users. And that's the worst case scenario. The best case scenario is that when you have full knowledge and you are able to coordinate all this beam scheduling mechanism. Mathematically, it's an MP complete problem, because you have a very kind of a configuration of all these beams. But basically what we find is that if we use this sort of distributed learning schedulings and different versions, we can get, in terms of a system spectral efficiency results, which are quite close to if you have full knowledge. So this seems promising, because it's also not using any it's using just this particular feature that all these technologies have to beam to users. So some future work going on. This is just to highlight this, that some recent work we are doing at, and this is the roof of my department. So we are basically, one of the interesting things that's happening here is that obviously great channels models have been developed. So by 3GPP and the Millimeter Magic project I mentioned, it just had finalized its final channel model, very comprehensive, encompasses the 3GPP channel model. So I invite you to have a look at that channel model. That's, I think, open source software as well. But the critic, even when we were doing that, was that when you're looking at sharing scenarios between say, satellite and say mobile, so you have, so this is, Yeah, this is an example of like interference scenarios that can happen. So if you have a satellite communicating downlink to a station, and then you have a mobile in 28 gigahertz or similar operating, and then that can cause interference. Now, these sort of scenarios, obviously, the ranges could be quite large, the interference range. And some of that is perhaps not fully encompassed in, when Military Magic we were looking at 200 maybe meters or 300 meters, so longer distances are perhaps something to consider. Also, because of the beamforming, you can have multiple passes, so you have multiple interference passes. So you need to consider this in this exotic. So what we are doing in Sussex, we are working with Plum Consulting, and we are doing measurements from the rooftop or Richmond building there to various other buildings and cars and so on, in order to basically get some more insight into this sort of interference scenarios, and this has also been fed into the I2R work. This is I borrowed it from my colleagues in Samsung just before I left. It is showing that basically these are about more complex channel model where you have to ground reflection also into account when you're looking at millimeter wave. Obviously, this is not totally beam formed, but it's a ground reflection. And when you basically add the ground reflection, then you get a lot of inference patterns. So the story becomes more complex. Okay, I think with that, I would like to conclude. I believe that the race for millimeter wave spectrum is ongoing in the US and is going to also intensify elsewhere as 5G progress. So this is a very interesting area to look at. I believe that millimeter wave bands offer new opportunities for sharing, both for licensed access and unlicensed. And from Sussex, we are contributing to this, and we are also delighted, obviously, to work with industry, SMEs, and academics. So thank you very much for your attention.
Okay. Have you got any questions?
Yeah, one question about beam management and beam cooperation. Do you consider training? Because currently in 5G standardization, training of the beams is one of the more complex problems. And the narrower the beams, the more complex and longer the training process is. So do you take this into your consideration, and do you have any algorithm of cooperation considering training?
That's an excellent question. In this particular study, we didn't consider training. So basically what the study does, let me just see. Okay, so in this example, we have a base station, a number of UEs, and then we just magically find the optimal beam towards that UE without doing the training part. So that's not part of this, because the focus was here more on the scheduling as such. But that's very interesting to consider. There is a bit of training in the sense that when they get feedback from the UE in terms of interference levels, and that is an input into the algorithm that find the optimal sequences. But it's always assumed an ideal beam is to each UE. Don't know if that answers your question.
That was extremely interesting.
Thank you very much.
Thank you very much. Okay.
Thank you.